Yes, hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. Today we're going to look at an additional concept under the concept of principles of quantum mechanics. And of course, this is a review of the de Broglie's hypothesis. Now, I've mentioned this concept in some of our videos under the concept of quantum mechanics. And I'd said that Louis de Broglie played a vital role in trying to give a vivid description of this wave-particle duality, whereby he gave a characteristic wavelength that can, of course, define or try to characterize the motion of small particles like electrons, protons, and neutrons, as I mentioned. So therefore, I argued that basically this particular characteristic wavelength can be expressed in terms of perhaps momentum. And we're going to see a specific conversion, which is going to be a relationship between Einstein's Planck's energy mass relationship, which is going to assist us develop the same. Now, Louis de Broglie argued that if we have these specific particles, which are mentioned as like an electron, which are of course a microscopic particle. We have an electron, proton, and then a neutron. These specific particles can be described in terms of a specific wavelength, if of course they are being described whenever they are under motion. And we're going to consider one of the aspects of or one of the particles of an electron, which is an accelerated under potential difference V, and we are going to see how we can describe them using Louis de Broglie's hypothesis. Now, Louis de Broglie relied on two specific, of course, laws, or as we can say, two specific theories, or perhaps laws from the two scientists which I had mentioned. The first one was Max Planck, whereby Louis de Broglie argued that basically from Planck's argument, Planck had said that a black body radiation consists of course, a number of oscillators, or a large number of oscillators whose energy can be described in terms of E is equivalent to hV given as such. And then we're going to look at also at Albert Einstein. Now, Einstein's argument from the photoelectric, or rather from this specific mass-energy relationship, Einstein argued that we can describe the energy of a body using energy is equivalent to mc squared, where c is the speed of light. And of course, so we're going to see that from this one, this is basically the concept of microscopic particles. And therefore, we're going to, as I mentioned, with this particular aspect of h is going to represent Planck's constant. And then we're going to have this one representing the frequency of this specific particle, which we are considering an electron in this particular case. And then we're going to have this one mass, which is mass basically of an electron, we're going to consider in this specific case. And then we're going to have this one representing the energy of this specific electron. And lastly, C is going to represent the speed of this electron, or maybe perhaps a photon, as we had, of course, described from Max Planck's quantum theory. Now, in this case, we're going to see that the relationship between the two is going to come up with what we refer to as a de Broglie's wavelength, which is going to be, of course, an equation representing a wavelength of a particle that is going to, of course, describe this particular aspect of the dual nature, or the wave-particle duality. Now, from this specific formula, we can give this one as formula 1 and 2. We can have a combination of 1 and 2 in order to describe this specific aspect of energy, since both of them are describing the energy of a subatomic particle like an electron, and therefore, or an energy of a photon. And therefore, we're going to have this one represented as hv frequency is equivalent to mc squared. So therefore, the energy according to Max Planck is equivalent to the energy according to Albert Einstein. But we had argued that we can represent this specific aspect of frequency of that photon as the ratio between the speed of light and lambda. So therefore, doing a substitution for this, we're going to have this one represented as hc over lambda is equivalent to mc squared. Now we can have a specific description for this specific part, or do a rearrangement for this specific part of the formula, and we're going to come up with a representation for lambda as a subject of this formula. So this is going to give us Planck's constant all over mc. So suppose we are to consider this specific particle as just as a particle instead of a wave. we're going to see that from classical mechanics, the product of the speed and mass is going to give us what we refer to as momentum. So this is going to describe the momentum of this specific particle, which is either a photon or an electron. And therefore, this particular formula is going to be given in terms of lambda is equivalent to h over p. And this is going to be what we refer to as de Broglie's. Of course, this is going to be referred to as the de Broglie's formula. And it's going to describe the wavelength of a particle that is, of course, under motion, and its characteristic, of course, wavelength. Now, according to him, we're going to consider an electron, as I said, and this electron is going to be accelerated under a potential difference V, which I mentioned, and we're going to see how we can have a different version of describing this specifically aspect of an electron that is traveling under potential in a potential difference V, which I've mentioned. I assume that we have understood this specific procedure for attaining de Broglie's equation, which basically represents the wavelength of this specific particle that it is, of course, under motional traveling, which can be represented in terms of a Planck's constant over momentum. And then, therefore, I've said that if we consider the electron that is being accelerated in a potential difference V, we can describe the energy of this specific electron using the product of its charge and that potential difference V given as such. And of course, if this electron is under motion, so this is going to be the energy. We can describe as well its kinetic energy using the normal description from classical mechanics, which is a kinetic energy is given as a half mv squared. So therefore, the energy of motion of this specific electron can be described in terms of a kinetic energy. And of course, therefore, we are going to have these two specific descriptions for this particular electron. And therefore, we can write that the energy EV is equivalent to the energy of motion of this particular electron given in terms of a kinetic energy, which is a half mv squared. Now we can have a manipulation of this specific formula so that we come up with a simplified version of describing this particular aspect of a momentum that we had given in de Broglie's equation. We had said that you can have this one, de Broglie's wavelength, given in terms of h over p. So therefore our task is to try and find out how we can describe the wavelength of this specific electron traveling in a potential difference v in terms of this description of energy. So this was a elimination of the Planck-Einstein's energy mass relationship, and of course we're going to see that this of course is going to be a description of the energy under potential difference in terms of EV and the kinetic energy. So this is going to give us a product of if we multiply mass on both sides, we can have another version of the equation given as MEV is equivalent to a half m squared v squared. But we had said that the product of mass times velocity is going to give us momentum, and therefore we are going to have this specific formula given in terms of this specific E. So this is going to be MEV is equivalent to the square of momentum, which is this specific section of the equation, divided by 2. So basically we can have the square of momentum given in terms of the square of momentum is equivalent to MEV. Therefore, momentum is given as the root of 2 MEV. So from the de Broglie's equation, then therefore we can have this wavelength of this particular electron being accelerated in a potential difference of V, given in terms of Planck's constant 1 over 2 MEV given as such. And this is going to describe a particular wavelength of this particular electron which is being accelerated under the potential difference of V. Now, having looked at this particular particle, as I've said, specifically as an electron, therefore we can do a substitution for these various constants that we have, whereby we have Planck's constant h, which is 6.625 times 10 negative 34, and then of course that is by 2, and then we're going to have this mass of an electron given in terms of 9.1 times 10 negative 34. So this is going to be negative 31 basically, kilograms, and then we're going to have the charge of an electron is equivalent to 1.6 times 10 negative 19 coulombs. So we're going to do a substitution for this specific constant, mass of an electron charge of an electron, but the V we are going to leave it as it is. So therefore we can have this wavelength represented in terms of a 6.625, and then we are going to have times 10 negative 34 divided by this is the root of 2 times the mass of an electron, 10 and negative 31, times E is the charge of an electron, 6 times 10 negative 19, and then that one times V. So the over of that one is going to represent the wavelength that is associated with that particular electron, and this is going to be in terms of 12.27 times 10 negative 10 all over the root of V, and that basically is going to be in terms of meters. So this one, having been a division of a unit of 10 negative 10, we can convert this one into angstroms, and therefore we're going to have a general description for this specific wavelength given in terms of lambda is equivalent to 12.27 all over the root of V angstroms given as such. So this is going to be a description of this specific wavelength apart from the Planck's Max Planck's Einstein's mass-energy mass relationship. We can have EV and the kinetic energy giving us the description of this version of the Broglie's wavelength for an electron in a potential difference V being given in this specific order. So the two are going to give us a basis for describing wavelength of this specific wave particles, and of course we're going to use this specific description whenever we're going to use the concept of quantum mechanics under the concept of a wavelength. So that is it for now, guys. Kindly check our description boxes for various links and subscribe to our channel so that you can be getting various updates on similar topics such as this one that we have already done. So that is it for now, guys. Bye, God bless you. Catch us in our next video.